Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class as a supplement. However, I'm putting it online just in case it would be helpful to others as well. There is a link to a printable set of guided notes that you can use to follow along with this video in the description. If you're one of my students, you should definitely have these notes printed because I did it for you as usual. Okay, section 3.2 is all about the word differentiability. And we're going to dive into a whole bunch of different problems where we'll see that word and, we'll talk about what to do with it. Before we move away from this title slide, though, I just want to point out to you that the background on the title slide is, I don't really know what it is. Maybe it's like sand or something. I'm not quite sure. But the important thing about it is that it's smooth. Doesn't it give off like a smooth vibe? Okay, that's on purpose because smooth is a way that you can describe a function that is differentiable. So in our opening questions, what does the word differentiable mean? A function that is differentiable, you can say has a smoothness to it, or we'll just say it is a smooth curve. Okay, that's a little bit weird. I'm going to try to write that again. Something happened. Anyway, moving on. Now, I read a little tiny bit on Wikipedia in my Calculus Just Explains It All video about differentiability, where mathematicians argued over what smoothness meant. And, they argued over was continuity enough to describe smoothness, and they decided that it was not. However, continuity is still important. Okay. Continuous. I can't write and talk at the same time because I won't remember how to spell things, but there we go. Continuous is a part of smoothness, a part of differentiability, but it's not all of it, as you will see. But still, it's important to note that you do have to have a continuous function for it to be differentiable everywhere. And finally, I just want to add one more little piece to this, and that is that for a function to be differentiable everywhere, let's say, then that means that the derivative of that function does not have any restrictions, or we could note that as the derivative exists. Okay, and if we're talking about like a function that's differentiable everywhere, then we would say that the derivative exists everywhere. So like an easy example of that is y equals x squared. If I take the derivative, which I know is 2x, I can easily see why the function y equals x squared would be called differentiable everywhere, because its derivative exists everywhere. There are no restrictions here. And if there are no restrictions on the derivative, then that definitely means that the function you were originally dealing with is differentiable, over the interval from negative infinity to infinity. All right, so let's take a look at the second opening question. We have a piecewise defined function here. G of x is 3x plus 2 for all x less than 1 and x cubed for all x greater than or equal to 1. And the question is, where is this function not differentiable? Why is it not differentiable at that point? Okay, well, for a piecewise function, you can look at each piece separately and first ask yourself, is each piece in itself differentiable everywhere? So left of 1, we have the function 3x plus 2, and that is definitely differentiable everywhere because it has a constant slope of 3 everywhere, right? X cubed is also differentiable everywhere. We haven't talked about the power rule in detail yet in any of our videos, but if you're in my class, we have discussed it at this point, right? And so we are going to make a little note here that the derivative of the derivative of x cubed is 3x squared. And that is enough to say, sure, that x cubed is differentiable everywhere because there are no restrictions on 3x squared. And so we know that the pieces separately are differentiable. So the only possible candidate for where it could not be differentiable would be that boundary point at x equals 1. So that's what we're going to look at. Okay, and this first little lesson, in this first problem, what I want you to know about being asked whether a function is differentiable or where it's not differentiable is the first thing you should always check for is continuity. And so that's what we're going to do at x equals 1. I can't, like I said, I can't write and talk. I'm trying to write the words check continuity. There we go. But again, we're just going to check that for now at x equals 1 because that's, the one place that we're looking at here. So to check continuity, what we could do is we could write a limit as x approaches 1 from the left of the function and a limit as x approaches 1 from the right of the function and see if those limits are the same and then identify the function value if we need to go that far. Let's see. Okay, so I'm going to write a limit as x approaches 1 from the left of g of x. And to evaluate that limit, I would be taking 1 and subbing it into the function that is less than 1 piece. So I'm going to take 3 times 1 plus 2. And I get a limit value of 5. Next, let's do the limit as x approaches 1 from the right. And if I'm coming from the right, that means I want to use the piece of the function where it is greater than or equal to 1 and sub 1 in. So I'm taking 1 cubed, and that is 1. And right there we can stop. We don't even have to move on to the function value because we can see that what we have here is a jump discontinuity at x equals 1. If there is a discontinuity x equals 1, that definitely means that this function is not continuous at x equals 1. Wait, of course it's not continuous. Sorry, I meant to say not differentiable at x equals 1. I'm sorry. I have actually been teaching all day and now I come home and I am doing a video lesson. So my brain is mush right now. Yay, we did it. All right, so we kind of like those. If it's not continuous, then it's not differentiable, and we can stop there. You're going to see at the end of this set of notes, there's another example similar to this, but it will be continuous, and we're going to have to move a little bit further to see why it's not differentiable. But we're not there yet. Let's do some easy stuff first. Take a look at this next little section where we have places where a function is not differentiable. Why is the F in function capitalized? I don't know, but let's just go with it. I think it's supposed to be a title, but more of those words should be capitalized if it's a title. All right, anyway, let's jump down here to number 3 because that's something that we were just dealing with. Anytime you have any type of discontinuity at a point, then your function is not going to be differentiable at that point. So we'll just label number 3 as any type of discontinuity. And you have plenty of examples there to look at, right? Any type of removable discontinuity, any type of jump discontinuity like we had in the piecewise in opening question number 2, or any type of infinite discontinuity will automatically disqualify a function from being differentiable at those points that are not continuous. Okay. Also, let's go to this one, number 2, because it's really easy to explain. This is a continuous function. This is like y equals x to the 1/3 power, or the cube root of x. But it is not differentiable still, even though it is continuous. It's not differentiable right here. This one is at x equals 0. And the reason is because the tangent line at that point would be a vertical tangent line. So if you were to zoom in on that specific point, you would see what the tangent line looks like, and what you would find is a vertical line. And we know that a vertical line, its slope is undefined, right? So let's call this a vertical tangent point, which is also a place that you need to be aware of that is not differentiable because the slope of a vertical line is undefined. Okay, finally, one other place where a function is not differentiable that you see up here in number 1 is any sort of sharp turning point, such as, like this is y equals the absolute value of x, or this one, which is more of a curved sharp turning point. It is actually y equals x to the 2/3 power. Okay, we usually call this one a corner and this one a cusp. If you want to write those words down, you can, but really it's just any sort of sharp turning point is not differentiable. And that one's a little bit trickier to explain. In my opening video for differentiability, I talked about zooming in on points like that, and you never see a tangent line. You never see one line that you would be taking the slope of. What you always see are two lines. And keep in mind that a derivative is a limit, and so it's a limit of a slope. And so if you have a slope on the left that is different from your slope on the right, then the overall limit slope, cannot exist. So that's one other place that we need to be aware of that is not differentiable. Any sort of sharp turning point. Okay, I just say it's sharp. It's dangerous. Stay away from it. So let's look at an example of that one right now. Take a look at example 1 with me. Find all of the points in the domain of f of x equal to the absolute value of x minus 2 plus 3 that are not differentiable. Okay, well, there's only going to be one, and we can find it very easily if we know that whenever we have the absolute value here, and we just have x to the first power, then that's going to be our typical v graph, our absolute value v graph. So I'm just going to do a little sketch. You could definitely get this pretty easily with your graphing calculator. However, this one's not too difficult to just figure out. The vertex of this v graph is going to be at the point 2, 3. So we have a shift of 2 to the right and up 3. Horizontal shift and a vertical shift. And here's the absolute value of x minus 2 plus 3 graphed. Again, the vertex of the v graph, the point there is at 2, 3. And so we'll go down here and we'll just say that that is definitely a place that's not differentiable, right? Now, when I ask you to identify points that are not differentiable, and you can see it in the wording where you see the word domain up here, that is just asking for the x coordinate. So to answer this, I'm going to say not differentiable at x equals 2. Yay, nice and easy. Okay, I should probably go back to this for just one more second and remind you of something that we've already talked about. We're going to talk about it in detail here. And that is that whenever you have a function that has a discontinuity, that is definitely not differentiable, but that is not the only criteria for something being not differentiable. You also need to look at sharp points, vertical tangent points, these things that we talked about right here. Corner, cusp, vertical tangent, that sort of thing. Okay, you need to keep in mind that these points are continuous, right? There is no break in this v graph. It is continuous, but it is still not differentiable at x equals 2 because of that sharp turn. So we have this theorem that we say differentiability implies continuity, or in other words, this is something that, again, if you're following along in the notes, as my students should be, you should write this down in the theorem box. If f has a derivative at x equals a, then f is continuous at x equals a. So what that means is if I say that a function is definitely differentiable at a particular point, then you can assume that it is continuous at that point, because continuity is something that you have to have for differentiability. If you need to pause the video for a moment to write that down, you can. Oh, well, you know what? I have more to say about this anyway. And the other thing that I want to say is that the converse of this theorem is not necessarily true. And so that's what I was sort of getting at with the absolute value graph, that v is continuous, but there is still a point where it is not differentiable. So you need to be careful about these words and not using them interchangeably. You need to understand what they mean, okay? If something is differentiable, it is definitely continuous. However, if something is continuous, it is not necessarily differentiable everywhere because you could still have something like a sharp turning point or a vertical tangent. Okay, so let's try to be clear about those words here in example 2. The graph of a function is given, and the question is, at what points does the graph appear to be? In part A, we'll say differentiable. In part B, we'll say continuous but not differentiable. And in part C, we'll say neither continuous nor differentiable. Now, this is not multiple choice, just so you know. We are identifying intervals or points, I guess, for all of these different parts. You can think of this as like a part A, you need to answer. Part B, you need to answer. Part C, you need to answer. And actually, I'm going to do these backwards, as I do a lot of things, you might have noticed. I'm going to start with part C, where we're asked to find points that are neither continuous nor differentiable. I like to start there because those are easy. Where are the breaks in your graph? Where are the points of discontinuity? That's what you're going to answer for part C. So I hope that you can definitely see. Let's draw an arrow. We really should have arrows on this. If it goes off the grid like that, you should just assume that it keeps going, okay? All right, I hope you can definitely see that there is a jump discontinuity at x equals -1. And so we can say that is a point where it's not continuous, but that also means it's not differentiable. So we label it as neither continuous nor differentiable. Okay, there is one other point of discontinuity that we can answer for part C, and it's right here, right? This vertical asymptote. Be careful. We have two different terms that use the word vertical. A vertical tangent is one thing. That is that is a continuous graph that just has a vertical tangent line at a particular point. This is called a vertical asymptote, which is, an infinite discontinuity. There's a break in the graph. Okay, so we'll go back up here and we'll say x equals 2 because it's a vertical asymptote is another place where it is neither continuous nor differentiable. All right, now let's go to part B. Where is it continuous but not differentiable? Okay, we have, I think, just one point. I'm going to grab my answer key just in case my brain's like still mush. No, I'm good here. Okay. There's one point that is continuous, but still not differentiable. Can you find it? It's at x equals 0. Do you see how to the left of x equals 0, you have a line, which, has a particular slope? I guess it would be a slope of what, like 2? And then on the other side, you have a curve, which is going to have a different slope on the right. So we're going to say that it's continuous, but not differentiable because it's a sharp turning point. And so we'll identify part B's answer at x equals 0. Finally, for part A, this had like a weird thing happen. Okay. Finally, for part A, where is it differentiable? Well, it's differentiable everywhere else. So this function, even though it's like weird, it has a ton of points that are differentiable. It just has 3 that are not. So to identify all of the points that are differentiable, we're going to need to use an interval for that. And we're just going to write an interval from -infinity to infinity that excludes these 3 points. Okay, so that could look like this. I'm just going to use like my interval notation here. I could say it is differentiable from -infinity to -1, put a parenthesis around -1 because we don't want to include it. Union that with a new interval, which starts with 1 and ends with 0. Again, parentheses, because we don't want to include these points. Union that with another interval that starts with 0 and goes to 2. Parenthesis there, because we don't want to include 2. And finally, union that with one more interval where we pick up with 2 and end with infinity. There's all of the points that are differentiable. Yay! Okay. In the next part, which is like a little U-try, but of course, because we are on a video, I will be going over it with you. I want to remind you of this. This right here is called a vertical asymptote, right? Which is just a type of discontinuity. Take a look at the U-try. Determine which statement best describes the graph of the function below at x equals 3. At x equals 3, you see that other term that uses the word vertical. This is called a vertical tangent. It's important to know the difference. If you were to zoom in right here, at that point, you would see a vertical line, and that indicates that the tangent line is vertical there. So we have a vertical tangent point at x equals 3. And that is continuous, but it's still not differentiable. So our answer is B. That's a little confusing also, like just going from this part A, part B, part C, where we answered all of them, to this where you're just determining which statement describes this. I know that's a little confusing, but this is like multiple choice where you need to pick one, and this was just multiple part where you need to do them all. Hope that makes sense. Okay, and then finally, as promised, I have another piecewise to end this little set of notes where we are again asked, where is this function differentiable and why is it not differentiable at that point? But what you're going to see is that when we check the continuity at this point, it's x equals 0, right? The boundary point. We will find that it is continuous. So we're going to have to move on a little bit more to explain why it's not differentiable. Okay, so once again, if we look at the pieces separately, x cubed is differentiable everywhere, and 4x is differentiable everywhere. However, they are splitting at x equals 0. There's a boundary point here of x equals 0. So that's our candidate for where it's not differentiable. And the first thing that I'm going to do over here for x equals 0 is I'm going to check the continuity of f of x at x equals 0. So just like we did in that warm-up problem, I'm going to look at the limit as x approaches 0 from the left. And that means subbing 0 into the less than or equal to 0 piece, which is x cubed, or we'll take 0 cubed and get 0. Let's put a line here. And then we will do the limit as x approaches 0 from the right of f of x. F of x. Use the greater than 0 piece, sub 0 in, 4 times 0 is 0. And finally, we need to make sure we do one other thing, and that is identify that it does have a defined function value at x equals 0. It definitely does because of the equals right here. You would use the equals, so sub 0 into x cubed one more time, and you get 0. And this is your definition of continuity at a point. If the left-hand limit, the right-hand limit, and the function value are all the same thing, then that function is continuous at that point. So it is continuous at x equals 0, believe it or not. Okay, but it's telling you that this function is not differentiable somewhere. So, we need to find that point. It is x equals 0, but why? Why is it, not differentiable at x equals 0? Well, keep in mind, you check for discontinuities. If there aren't any discontinuities, there's still two other things you can check for, and that is, are there any sharp points or are there any vertical tangent points? We're going to focus on sharp points because often with piecewise functions, when they come together at the pieces, if they do come together, it could be at a sharp turning point or a quick change. Okay, so the next thing that we're going to do is we're going to check the derivatives at x equals 0. Okay, we're going to check the left-hand derivative at x equals 0 and the right-hand derivative at x equals 0. Now, I think before we actually plug 0 in, we should just define our derivative equation as a piecewise function. And so we're going to go to each of these pieces and take the derivative. The derivative of x cubed is 3x squared. Now, what I'm going to say at the boundary point x equals 0 is for all x less than 0, but I'm going to drop that equals because I'm not sure if the derivative is even defined at x equals 0, so I don't want to bring along the equal sign. On the other side of x equals 0, the derivative of 4x is just 4, and that is for all x greater than 0. Now, I'm going to show you some notation that I don't know if I made it up or not. I am pretty sure in my mind I've made this up, but then I actually think I saw it somewhere. I don't know. What I need to do now is a left-hand derivative and a right-hand derivative at x equals 0, and I have these quick little shortcuts to do that, so I don't need to write like left-hand limits and right-hand limits. So I want to show that I am finding the f prime value for 0 from the left of 0. And so I just put a little minus sign right there. I call that my left derivative. Again, I don't know if I made that up. this notation or not, but I like it. This is like one of the only places I ever use it, but I like it. All right, so I'm going to plug 0 into 3x squared, and 3 times 0 squared gives me a left-hand derivative value of 0. That says left derivative, by the way. Okay, next, I'm going to find the right-hand derivative, and so I'm plugging 0 into f prime, but I'm going to put a little plus sign here, which indicates I'm doing a right derivative. Okay, the thing about that is, though, you don't have an x to plug into the right. It's just 4. There's your derivative. Finally, since these don't match, the derivative values don't match on the left and the right, that is enough to indicate to you that there is a sharp point there. And so, because these do not match, what you can say is that there is I'm going to put it up here because I know my picture's somewhere down here. And I can't remember how to remove it right now because, again, my brain is jello. There is a sharp point at x equals 0, therefore not differentiable at x equals 0. Yay! Ta-da! We are done. As usual, I hope this video was helpful. Bye!